Welcome everyone. Today we are diving deep into a fascinating mathematical experiment that combines geometry, probability, and a bit of randomness. This experiment, known as Buffon needle, was first proposed by the French mathematician Georges-Louis Comet de Buffon in the 18th century. It provides a surprisingly effective way to approximate one of the most important constants in mathematics, pi. Use just a needle, some parallel lines, and a bit of chance. Sounds simple, right? But the results can be profound. Before we get into the experiment itself, let's take a moment to appreciate why this is so special. Pi, a number that you have likely encountered in school, shows up in so many places, from the area of a circle to waveforms in physics to even the behavior of certain random processes. So, how could a simple experiment with a needle be used to estimate pi? Today, we are going to break it down step by step and show you how the simple, seemingly random dropping of a needle can lead to one of the greatest constants in mathematics. Now, let's begin by understanding how this experiment works and why it's so intriguing. We'll also see how it ties into some powerful mathematical ideas like probability and calculus.
All right, let's dive into right in the experiment itself. Imagine we have a needle of length L and a floor with parallel lines spaced at a fixed distance as d. The question we want to answer is, what's the probability that the needle will cross one of these parallel lines when we randomly drop it onto the floor? Sounds simple enough, but here is when it gets interesting. The probability is related to pi. So how do we make the connection? Well, it turns out the probability that the needle crosses a line depends on three things. Length of the needle, L, that's L, the distance between the parallel lines, that's D, and pi itself. So the key equation is probability equals to 2 multiplied by L divided by pi into D. This formula is fascinating because it tells us that the probability of the needle crossing a line is directly proportional to pi. In fact, by performing the experiment enough times and counting how many times the needle crosses the line, we can estimate pi. So, why does this work? The maths behind it is rooted in geometry and probability theory. The random dropping of the needle is a type of random event we can model mathematically. In fact, the connection between randomness and geometry is a beautiful application of what we call stochastic progress process, a part of probability theory. Now let's explore how we actually conduct the experiment and what we need to set it up.
Now let's talk about how to set up the Buffon's needle experiment. You don't need anything fancy. To start, you need a needle or a stick, a piece of string, or even a straw will work. Just make sure it has a measurable length. Next, you need a flat surface where you can draw parallel lines. The distance between the lines is crucial. You need to space the lines evenly apart. But the important thing is that the distance between the lines should be greater than the length of the needle. This will allow the needle to cross the lines in various ways. Once you have drawn your lines, we need to make sure that the needle drops randomly. This is essential because if there is any bias in how the needle falls, your results will not be accurate. The more random your drops, the more closely your results will match. Let's dive deeper into the concept of randomness. In mathematical terms, randomness refers to an unpredictable or unpatterned event. For this experiment, we are relying on what's known as as a uniform random distribution, meaning that every possible outcome or every possible position and the angle the needle could land in has the same likelihood of happening. Alright, so we have our setup, the needle, the parallel lines, and a random method of dropping the needle. But to make this a valid experiment, we need to repeat the process many times, ideally hundreds or even thousands of times. Each time we drop the needle, we record whether it crosses the line. The more drops we perform, the more reliable our estimate of pi will become.
Now comes the fun part. Conducting the experiment, we will drop the needle multiple times and count how many times it crosses the one of the parallel lines. Here's the process step by step. Toss the needle onto the floor. Observe whether the needle crosses one of these lines and repeat this process the number of times. Each time the needle crosses a line, we add 1 to our count. The more drops we make, the better our estimate of the probability of crossing a line will be. Let's say we perform 100 drops. If the needle crosses the line 50 times, that gives us the probability of 50 by 100, that is 0.5. Now let's see how this probability ties into pi. Using the formula we discussed, that is pi is equals to 2 into L divided by probability into D. We can plug in our probability, the length of the needle and the distance between the lines to estimate pi. The more times we repeat this process, the the closer our estimation will get to our true value.
That's about the mathematical formula and data analysis. Let's take a closer look at the math behind this experiment. The beauty of Buffon's needle is that it connects randomness with a mathematical constant. If we were to perform this experiment of times, our probability value would converge to a precise estimate of pi. Here's how we can calculate pi from our experiment. We can conduct many trials, say 100, count how many times the needle crosses a line. We calculate the probability of crossing a line, which is simply the ratio of crossing to total drops. Let's use the formula again to estimate value of pi. Pi is equal to 2 into L divided by probability into D. As we repeat the experiment with more and more drops, the estimate will get more accurate. Over time, our experiment value for pi will approach the true value of pi, that is approximately 3.14159. This is an incredible example of how probability theory, a branch of mathematics concerned with random events, can be applied to solve the real world problems and even calculate something as fundamental as pi.
So, what does all this tell us? Buffon's needle is a perfect example of how we can use random processes to gain insight into deterministic quantities like pi. It's also a great way to understand Monte Carlo methods, a class of algorithm that rely on repeated random sampling to obtain numerical results. Through this experiment, we can approximate pi and we can see how probability connects to geometry. The more we rely on randomness, the more accurate our estimation of pi becomes. This is a concept in both probability theory and calculus. It's the law of large numbers at work. The more trial we conduct, the closer we get to the true value. Isn't it amazing that something as simple as dropping a needle can teach us about convergence of random events to determine values, to deterministic values?
To summarize, Buffon's needle is not just a quirky experiment. It's a profound lesson in the power of probability, geometry, and randomness inherent in nature. As we increase the number of trials, the estimate of pi converges, demonstrating how randomness can be harnessed to uncover the mathematical constants. By repeating the experiment enough times, we approach the true value of pi, which shows the beauty and power of mathematics, especially in probability theory. Thank you for joining us on this fascinating journey into probability, geometry, and pi. We hope you have enjoyed learning how simple experiments can reveal deep truths about the world around us.
Explore, experiment, and let randomness guide you to the beauty of mathematics. Until next time, keep dropping those needles.